Okay, welcome to this tutorial session. So we're going to be looking at question number 4, and the question reads as follows. Two blocks with masses M1, which is equal to 3.2 kgs, and M2, which is equal to 4.5 kgs, are touching each other on a frictionless table. If the force F, which is pushing the masses M1 and M2, which are touching each other, is equal to 6.8 newtons. What is the acceleration of the two boxes, and what else are the questions? With what force does M1 push against M2? So that's the first part of the question. So it is very important to be aware that in this case, things are much easier in that we are dealing with a frictionless table. Now, in reality, this kind of a table does not exist because friction is always present, even in a very, very small amount. So, this problem with friction, without friction, actually makes things much, much easier. It means that we have to consider one less torque. In this case, we have to forget about friction being neglected. Okay. So we do not have to worry about the force which is trying to oppose the motion, which in this case is friction. Now, when you apply a force, since we only have one force, and these masses M1 and M2 are going to be sliding on this table, so they will only be moving in the horizontal direction. So when you apply this force, the amount of force which you apply determines, according to Newton's second law of motion, determines how much acceleration the body is going to undergo. Okay, so the acceleration in this case is proportional to the mass. However, the acceleration also depends, the acceleration in this case is proportional to the force. So the greater the force, the more acceleration the body is undergo. However, the acceleration also depends on the mass, in that the more mass you have, then the less acceleration you undergo. Okay, so in this case, since these two bodies are touching, for us to find the acceleration, we need to work out what the total mass of these masses is. So in that case, that's where we come in here. We work out the combined mass of M1 plus M2, which is 3.2 kgs plus 4.1 kgs, and that gives us a combined mass of 7.3 kgs. Since these two masses M1 and M2, if they are pushed, when they are pushed by this force F, they move to the right. Okay, we therefore take this direction, the right, in which they're going to move, the direction of motion of the masses, to be our positive x direction, and the opposite direction to be the one on the left to be our negative x direction, and we're going to stick to that direction throughout as we try to solve this problem. The reason why direction is important in this case is because, one, we are dealing with force, which is a vector, and also we're dealing with acceleration, which is a vector. Okay, vectors have got size, which is magnitude. They also have direction. So we need to have a sense of direction. In which direction are these masses going to move once this force is applied on them? Okay. So now that we have got the combined mass of the masses M1 and M2, which is 7.3, we proceed to apply Newton's second law of motion. Newton's second law of motion gives us a relationship between the resultant force, or the net force which is acting on the body, or the net force in this case acting on these two masses M1 and M2, and the acceleration which these two masses are going to go. So since we in our case along the x direction, there's only one force which is present, which is this one, F. We do not have friction present to oppose the motion which is going to come about, because we are dealing with a frictionless flow. So there is no friction present here. The only force which The only external force which is present in this case is the force F, which is 6.8 newtons. So that is our resultant force. And since it's pointing to the left, we take our resultant force to be positive. In the case of the mass here, the mass which is undergoing the acceleration, okay, in our problem, we are not dealing with just one mass. We are dealing with two masses. So the total, we have to use the total mass here, which is the 7.3 kgs which we have obtained, then multiplied by the acceleration which these two bodies are going to undergo. The acceleration which these two bodies are going to undergo, M1 and M2, is going to be the same. Okay. So our net force in the x direction is the 7.3. That's our force in the x direction there. Then the combined mass of the bodies, which is M1 plus M2 times acceleration. So in our case, the net force is 6.8 newtons, then equals to the combined mass of the two masses, 7.3 times the acceleration, which the bodies are going to undergo in the x direction, making the acceleration the subject of the formula. We end up having ax is equal to 6.8 newtons divided by 7.3, and we get ourselves a value of acceleration which is 9.3 meters per second squared. So when this force of 8.6 newtons is applied on these masses, both M1 and M2 undergo an acceleration of 0.93 meters per second squared. So in this case, the acceleration is the same for the two masses. Okay. Next thing is, with what force does M1 push against M2? Now, the force which an object experiences, regardless of whatever is causing it, the force which an object experiences is equal to the mass of that object experiencing a force. So in this case, we are talking about M2. M2 is the one which is being pushed by M1. So the force which M2 is going to experience is equal to the mass of M2, which is this, multiplied by the acceleration. The acceleration of these two bodies is the same, which we have already found here to be 0.93 meters per second squared. So the force exerted by M1 on M2, denoted F12, is the product of the mass of the second mass, the second mass M2 times the acceleration. Always the force which a body experiences is related to the mass of that particular body and the acceleration which that particular body is undergoing. M2 has got a mass of 4.1, which is what we have here, multiplied by the acceleration which is actually undergoing, which is 0.93 meters per second squared. Therefore, the force which M1 exerts on M2, we get it as 3.812 newtons. Part C. Part C reverses this problem. Okay, the problem is reversed with part C, in that the force is turned, it's reversed. If the force is turned and reversed, then our force points in the negative x direction. And since there is only one force present, this force becomes our resultant force and is going to be negative because it's now pointing in the negative direction. And of course, this force, as we have seen before, is acting on a combined mass, a mass of M1 plus M2, which the combined mass being 7.3 kgs. So our resultant force, or net force in this case, is pointing in the negative direction, and the only contribution to the resultant force is F, so we end up having minus 6.8 newtons. Again, if we apply Newton's second law of motion, that allows us to obtain the relationship between the resultant force, the masses on which the force is being applied, and the acceleration which these masses undergo. So in this case, since the only contribution to the resultant force is minus F, So we end up having that minus F, and
yeah.
Okay. Can you see the presentation? Yeah. So we end up having negative force minus 6.8, and the combined mass m1 plus m2, which is 7.3, then the acceleration in this case, like that. Okay. So next, the resultant force is negative because it has been reversed, and it's the only force, that force F is the only force which is present. So after it has been reversed like this, the combined mass doesn't change. Whether you reverse the force or not, the total mass is the same. However, the acceleration is going to be different because the acceleration depends on the force, depends on the direction of the resultant force. So in this case, for us to work out the acceleration, we make it the subject of the formula. We have AX is equal to minus 6.8 newtons divided by 7.3. And we end up having an acceleration AX, which is minus 0.93 meters per second squared. This is the force this is the acceleration which both masses m1 and m2 undergo if the force is reversed. As you can see, the size of the acceleration, 0.93 meters per second squared, is the same in A and in C. The acceleration is the same. The size, the magnitude of the acceleration is the same. The only difference is the negative sign, since acceleration is a vector. So in this case, the body accelerates in the negative direction. The force exerted by M2 on M1 is denoted F21 and is given by the mass, by a product of the mass, which is M1. M1 is the one experiencing this force times the acceleration which we have found here. So in this case, this force F21 is going to be equals to 3.2 kgs times minus 0.93 meters per second squared, and that gives us a force F21 of minus 2.973 newtons. If you look at these two forces we have found, F21 is 3.813 newtons and it's positive. Then F12 is 3.813 newtons and it's positive, and F21 is minus 2.973 newtons and it's negative. The size of these forces is not the same. The direction is different. The reason why the size is not the same is because the force depends on the mass of the body which is experiencing that force multiplied by the acceleration which the body is undergoing. In both these cases, the size of the acceleration is the same. The only difference is the direction in which the bodies are accelerating. And that's the reason why we have got two different forces. Is that clear? Any questions? So this problem is quite short, and of course it looks much shorter because I had tried to do part of it yesterday, but again internet disappeared. Okay, so as per the promise, I can only do one question, and that's what I'm prepared to do today. So we'll continue tomorrow. We'll try to look at question number 5. Try to work out question number 5 tomorrow. Are we clear?
Yes, sir. But this is when I was just starting. And then I heard that you're saying that we're going to continue tomorrow.
Yeah, because people didn't come, so I just decided to record a video. So I think you will have to watch the video, which I'm going to upload to YouTube. Is that clear?
Yes, sir.
Okay, so I'm going to upload the PDF to Moodle and also the video to YouTube so that you can rewatch it, because I had started earlier since, yeah, time stuff, and I have to be somewhere else now.
All right.
Okay, all right, good night.